Hello, in this lecture, we are going to start with one of the very beautiful questions that was asked in TIFR 2018 examination. And it was about the thing that we are discussing right now, that is the Fourier expansion only. Okay. So right now, as you're aware, that we are studying Fourier expansion. And this particular question was asked in TIFR 2018. Okay. So the first thing is, the question says that the Fourier series which reproduces in the interval from 0 to 1 the function this. So basically what is it is requiring? It is requiring a Fourier series representation. It requires us to write a Fourier series representation of this particular function. That is from n equals to minus infinity, n equals to plus infinity, Dirac of x minus of n. Okay. Now you see this particular function is in literature, it is referred to as Dirac Comb. This is referred to as Dirac Comb. And why it is referred to as Dirac Comb, you will come to see here. See, what will happen? So it will, if I plot this particular graph, you will be finding that you will get a comb-like structure only. Okay. So what will happen? You see, what does it mean? I'm just writing it here. So what does it mean? If I'm writing summation Dirac of x minus of n, where n belongs to z, from minus infinity to plus infinity, it would mean dash from minus infinity. So let's write Dirac of x minus x plus 3 plus Dirac of x plus 2, then plus Dirac of x plus 1 plus Dirac of x plus Dirac of x minus 1 plus Dirac of x minus 2 plus Dirac of x minus 3, so on and so forth. And then you will have this till infinity will go from minus infinity to plus infinity. Okay. So this is how it is. So basically, what does it mean? It means that your Dirac delta function is situated at x equal to minus 3, Dirac delta function is situated at x equal to minus 2, Dirac delta function is situated at x equal to minus 1, so on and so forth. So basically, what will happen? You'll have all sort of narrower spikes at all of these integers. Okay. At all of these integers, you will have these narrower spikes, and these are of unit strength. Okay. These are of unit strength. So you'll have one narrow spike here. Then, okay, so you'll have another narrow spike here, again a narrow spike here, again a narrow spike here, and all these points are integral points. Okay, so at all of these integral points, you will find that you have these narrower spikes, and these are infinitely extending. And secondly, not only infinitely extending, but also we could say that they're of unit strength. So you just keep it quite close. So basically, you have to mind the gap. So basically, in each of these, the gap is equal to 1 only. So just don't get confused. So it seems as if it is a as if it is a comb-like structure. So basically, here also there will be a you can say narrower spike. So basically, this is at x equal to 0, this is x equal to 1, this is 2, this is 3, this is 4, this is 5, this is minus 1, minus 2, minus 3, so on. So basically, this type of structure is called as your Dirac Comb structure. And you can see clearly that the periodicity of this particular function is 1. That at exact equal to 1, your function is getting repeated. Exact at translation x equal to 1, your function is again a narrow spike. Again, if you add like x plus 1, again there is a spike. Again, you add a 1, translate your function with t equal to 1. So you will find that these narrow spike would come. So basically, this is Dirac Comb. And Dirac Comb has a periodicity. It has a periodicity. It has a periodicity t equal to. Okay. Now, why I'm pointing towards periodicity is, see, what needs to be seen is that I know that if my function is periodic, so I'm just writing here. This is something that I've already taught you, but just for revising you. So if fx has finite number of discontinuities, and it's not necessary that it may have always discontinuities, but if at all it has finite it has discontinuities, then it must have a finite number of discontinuities in one period. In one period, and you can say that it is a periodic function. Particularly, it is a periodic function. It has some At max it can have only finite number of discontinuities. Then this particular function can be represented as in terms of Fourier series, or more appropriately I would write complex exponential Fourier series. So it can be represented as minus infinity to plus infinity Cn exponential of iota 2n pi x upon t. So this is how you can represent your function in terms of complex exponential series, complex exponential Fourier series, I would say. Okay. Now you see, we have to write the function f of x, which is actually Dirac summation n belongs to z, Dirac of x minus of n, and we have to write the Fourier representation of this particular function. So what Fourier series representation to this particular function? So what I'll do, I will try to find Cn. So what is Cn? Cn is equal to minus t by 2 to plus t by 2, and you have this f of x here, and then exponential of minus of 2 n pi x upon capital T, and then you have this dx. Okay, and if you see, if you again, I'm just trying to, let me try copy this up. Okay, just give me a minute. It's copied, then it will be good. Okay, it's not getting copied. Okay, so if you can see, sorry, if you can see what is x equal to minus half, x equal to half is here, x equal to minus half is here. So here you have function is 0, here your function is 0, and only the function that is there, like here it is 0. So basically integral would not contribute. Here it is 0, integral would not contribute. But here at x equal to 0, there is a Dirac delta function. So basically, if I integrate from minus half to plus half, it is equivalent to integrating from minus half to plus half. And remember, t is equal to 1. So therefore, I'm writing minus half to plus half. And this will be Dirac of x. And this will be exponential of minus of 2n pi x dx. See, what I have done, I have written t equal to 1. Why t equal to 1? Because t equal to 1 is the period of the Dirac Comb function. So basically, the period of this particular Dirac Comb function is equal to 1. So, and I have to find these Cn's. If I am able to find Cn, then I may write my function in form of this particular complex exponential series. So basically, this is your function, point number 1. And you have to write this function in terms of a complex exponential series for which you require this C of n. So basically, you require Cn there. If you do not have Cn, then you will not be able to find it. So basically, it is equals to minus half to plus half. And this Dirac of x. So basically, if you remember a formula that I told you, which is called as the filtering property. So if I am integrating Dirac of x minus x naught times fx dx, what do I get? I simply get f of x naught. Similarly, here I will simply get, because x equal to 0 is situated between minus half to plus half, you will simply get e to the power minus 2n pi, and here you will have a 0. So basically, it will be equal to 1. So here all the Cn's for all n belongs to z will come out as 1 only. In other words, now if you want to write your function f of x, this is equals to n equals to minus infinity to n equals to plus infinity, Cn is equal to 1, and here you have this exponential of iota 2n pi x, and then t is not there, so forget about it. What you're going to get, so basically what you can do is keep it, see this from here you are, what is happening, so I'll write it minus, so I'll write one thing, exponential minus of 6 pi iota x. Basically, I've placed n equal to minus 3. Then, and there would be some terms on the, like, so you'll have terms from minus infinity to plus infinity. I'm just showing a few terms. 4 pi x plus exponential minus 2 pi x plus exponential 0 plus exponential iota 2 pi x plus exponential iota 4 pi x plus exponential iota 6 pi x, so on and so forth. So basically, this is how you're going to get. Otherwise, what I can do is I can write this particular thing as 1, because this is 1, exponential 0 is 1, then plus exponential minus 2 pi iota x, exponential iota 2 pi x. This will give you 2 times cos of 2 pi x. This is something that you know, that e to the power iota theta plus e to the power minus iota theta is simply 2 times cos theta. So using this, I'm getting 2 cos 4 pi x plus 2 cos 6 pi x, and then you have to run till infinity. So basically, so there your summation, that is Dirac of x minus n, that is the that is the Dirac Comb. The Fourier representation for this Fourier series representation for this Dirac Comb function is simply 1 plus summation n equal to 0 to infinity and n equal to 1 to infinity 2 times, I'll write 2 outside, in fact, cos of 2n pi x. So this is how you can write your Fourier representation, Fourier series representation of the Dirac Comb function. Okay, so this was asked in your net exam, in the TIFR examination of 2018, and it's quite easy to see that option number, I think B is correct. Okay, now what physically, if you can see what is happening. So what is happening, that all these cosines are superimposing with each other with all different frequencies. So basically, it represents the superposition of cosines of varying frequencies. So by actually altering n, we are actually playing with the frequency of this particular cos function. So basically, we are superposing all sort of these cosines of varying frequency, and what we are getting that all of these cosines interfere destructively. Why interfere destructively? Because see, after all, your initial functions were some cosine function, right? And if you're adding all of them, what is happening? All different frequency, when you add, this actually is giving you a Dirac Comb function. This is what it means now, because Dirac Comb function, the Fourier representation is basically equivalent to adding superposing all sort of cosines of different frequencies. And obviously, all sort of cosines means the frequencies of frequencies like 2 pi, then you have this frequency 4 pi, so on and so forth. Okay, so all these cosines interfere destructively to give rise to, or you can say leaving behind, we'll write it so that leaving behind only you can say sharp Dirac delta functions. Sharp Dirac delta functions at integral values of x. So this is how it is. So basically, what is happening? So this is how you write the Fourier series representation. This is how you write the Fourier series representation of the Dirac Comb function. This was asked in your TIFR examination. I hope you might have got the question. And if there is certain doubt, please let me know in the comment section. Till then, take care. Bye-bye.